Bienvenidos todos. Quizás sepan ustedes que este año 2015 ha sido declarado como el Año de la Luz por la UNESCO. Nosotros durante toda esta semana hemos tenido el privilegio de tener en el Donostia International Physics Center, en el DIPC, a una persona que yo creo que consideraría uno de los mejores físicos que hay ahora mismo en el mundo. Y creíamos que con motivo del Año de la Luz, ese privilegio deberíamos compartirlo pues, con todos ustedes. Esa es la razón por la que hemos invitado a David Wineland a dar una charla hoy aquí. Y además tenemos un privilegio adicional, que es que la persona que va a presentar a David Wineland es el diputado general, Markel Olano. Así que, Markel, muchas gracias por estar aquí con nosotros en este acto y adelante. Bueno, perdón, solo una cosa, se me había olvidado un asunto práctico, que se me había olvidado, que si no me echan bronca. Canales de traducción. La charla va a ser en inglés, van a ser aproximadamente 45 minutos. El canal número 1 es el canal en castellano, el canal número 2 es en inglés y el 3 es en euskera. ¿De acuerdo? Sorry, Markel.
Eskerrik asko. Arratsalde guztioi, ez zarete niri entzutea etorri, beraz labur egingo dut. Lehenik eta behin, esan beharra daukat niretzako David Wineland irakaslearen aurkezpena egitea gore handia dela, eta eskerrak eman dizkiotela baita ere DIPC-ri, Donostia International Physics Centerri gonbidapena luzatu didalako honetarako. Eta esan beharra daukat labur, ni nire honi eta uste dut gudanak ere arro egoteko garela, DIPC bezalako zentrua daukagulako hemen Donostian, Gipuzkoan, Euskal Herrian, hain zuzen ere, materialen fiziken arloan erreferentziazko zentru badalako naziarte osoan, eta uste du gainera eredu badala Euskal Herri mailan dauden ikerketa zentruentzako eta bide beretik jarraitzeko benetan argi oso indartsu bat eskaintzen duela DIPC-ek, beraz gaurko hitzago probestu nahi nuke hori eskerron hori egiteko eta rekonozimentu ere egiteko DIPC-ri. Por otro lado, sería, eta baita ere, onartu baita ere, eta eskerrona eman Pedro Miguel Etxenik eri, gaur ez dago hemen gure artean, baina berak ere dauken lidergo paperaren gatik. Y simplemente decir que para mí es un honor estar aquí entre ustedes presentando a David Wineland, ganador del Premio Nobel de Física de 2012 por sus trabajos experimentales con partículas cuánticas. El profesor Wineland obtuvo su licenciatura en física en la Universidad de California, Berkeley, en 1965 y finalizó su doctorado en 1970 en la Universidad de Harvard, desarrollando una tesis doctoral titulada El máser atómico de deuterio. Luego trabajó como investigador postdoctoral en la Universidad de Washington y el profesor Wineland trabaja actualmente en la Universidad de Colorado y en el Instituto Nacional de Estándares y Tecnología del Departamento de Comercio de los Estados Unidos. Wineland es miembro de la Sociedad Americana de Física, la Sociedad Óptica Estadounidense y fue elegido miembro de la Academia Nacional de Ciencias de Estados Unidos en 1992. Seguro que todos ustedes sabrán mejor que yo que sus descubrimientos han sentado las bases de la actual investigación fotónica, permitiendo así el avance producido en los ordenadores cuánticos ultrarrápidos y los relojes cuánticos ultraprecisos. En los próximos minutos tendrán ocasión de profundizar en la materia y de escuchar en primera persona la experiencia del propio Wineland. Professor Wineland, thank you for coming to San Sebastian. Eskerrik asko. Please.
So, okay. So, Escarigasco, and now I have to apologize because that's the only word I know in Basque. So, it's advancing here. Oh, there, now it's finally caught up. Okay. So anyway, it's a pleasure to be here. I've been visiting the university and the Center for Quantum Physics this week, and it's my first time in the Basque Country, but I've certainly enjoyed my visit, both the science and the food. So anyway, so if you don't understand this cartoon, I hope that maybe during my talk you'll get an idea of what this cartoon is about. So to summarize, I'm going to try to give you an idea why quantum is interesting for... Oh, sorry. Okay. So I'm going to try to give you an idea why quantum is interesting for computers. I'm going to describe this idea of quantum superpositions and the example that Schrödinger came with, his cat. And I'll tell a little bit about how we manipulate quantum states, and I'm going to tell you more about my involvement in this, but there's certainly many people involved with this subject. And I'll try to just give you a rough idea of what the quantum computer is about, and then relate that back to Schrödinger's cat. And in the end, I think it's always fun for a general audience to tell you a little bit about what the Nobel Prize ceremonies are like. So one way to motivate why we have to think about quantum effects in computers is something is related to what's called Moore's law. And it's not really a law, but it's a trend that's held true for several decades now, where basically the statement is that the amount of logic gates or transistors on a computer chip doubles roughly every year and a half. And this is an example of exponential scaling. And of course, it's responsible for the great power that our iPhones and laptops have these days. But one interesting thing is if this trend, this Moore's law, continues to go along as it has, then roughly in 10 or 15 years or so, we're going to get down to where the size of the transistors, the logic gates, are near the atomic scale. And there we have to confront fairly directly the quantum effects. And so one thing we've been thinking about, we as a group, is that maybe we can take advantage of some of these quantum effects, and one is superposition. So I'll try to, I realize most of you aren't physicists, but let me try to give you an idea of this concept of superposition. And one, I think, fairly good example is if you look at this image up here of a box, if you, at some instance of time, you might see this face be in the foreground, and at other instance of time, you might see that face be in the foreground, like these two examples down here. So in some sense, this is neither one or the other, it's both at the same time. And so this is, I think, a good example to this idea of superposition, that it's where an object can share two properties simultaneously. The other thing, which I won't say a lot about, but this example is actually a fairly good analogy to what happens when we measure quantum systems that might be in superpositions. When we measure their state, they collapse, or we say they project onto one state or the other. And I think that, so this idea where when you see this image up here be in one orientation or the other, that's gives you a good sense of the way projection works, that when we do a measurement on a system, it'll go into one state or the other and not be both states at the same time. So very briefly, I certainly can't describe all the elements go into a quantum computer in this short amount of time, but I'll try to give you a sense of why it looks interesting to us. And one is, again, that we can, in this same idea of superposition that I just tried to describe in the last view graph, a classical computer, of course, most computers work on the binary system, so the basic elements of memory are either a 0 or a 1. But in this superposition sense, we can get a quantum bit to be both a 0 and a 1 at the same time. And where this starts to look interesting is if you consider how a memory based on this quantum superposition might scale with numbers. So, for example, for a 3-bit register, for our ordinary computers, your laptops and PCs, a 3-bit register will represent one possible number, say 101. But in this superposition sense, a 3-bit register could simultaneously represent all the numbers from 000 up to 111. And this is an example. So this is 8 possibilities, or 2 to the 3, 2 to the number of bits. And this is an example of exponential scaling. And a dramatic example is say for 300 bits. Now 300 bits in your PC might hold about a line of text. But in this superposition sense, the 300 quantum bits will store 2 to the 300, which is about 10 to the 90th, which is more than all the elementary particles in the universe. And so in some sense, this quantum memory can store more information than a classical computer if you took all the matter in the universe. So that sounds pretty good. Another thing is that when we operate on these states, when we do, say, just a simple operation of flip one of the bits, it basically operates on all of these numbers at once. Well, it turns out in quantum mechanics there's a rule that we have to abide by, and that is measurement. And just as in the example as I explained before, where a box may be in some superposition state, when we measure it, it'll collapse onto one orientation or the other. Similarly, for the quantum bits, when we measure this register, each bit will collapse onto 0 or 1, not be both and 1. So for example, in this 3-bit example, when we do a measurement on this quantum register, we're only going to get one of the possibilities. And that is a severe restriction, but there was a computer scientist about 20 years ago. His name is Peter Shor, and he came up with an algorithm saying if we could make this quantum computer, one of the applications would be that we could factorize large numbers. And what that means is if you have a very large number, which is the product of 2 smaller numbers, then you can find those factors. And this becomes a very difficult problem in mathematics when the numbers become hundreds of digits long. And in fact, one reason this is important is basically all modern encryption, secret coding, is done with an algorithm that would be, the security would be lost if you could efficiently factorize large numbers. So for example, when you buy something with your credit card, the security is derived from the same algorithm that would be compromised by a quantum computer. And of course, government secrets are also encoded this way. So it's a major problem that governments would certainly be interested in. So let me give you a couple of other examples of this idea of superposition, because it certainly makes no sense in our everyday experience. And one example of that is we can, in our experiments, we use atoms, they're charged atoms or ions, and we can store them in what we call a trap. And a good analogy to this atom in the trap is it's like a marble in a bowl, and the marble can, say, roll back and forth. And so at one instant of time, it may be on the right side of the bowl, and the other instant of time, it may be on the left side of the bowl. But with our atomic marble, we can create a situation where it's both on the right side of the bowl and the left side of the bowl at the same time. And of course, as I say, this makes no sense in our ordinary day experience, but this is the world we actually live in. This is a good example of this idea of superposition. There's another case which will be more relevant for the quantum computer that we're trying to make, and that is that when we represent energy states in a system like an atom, they tend to only exist in certain discrete states. So for example, an atom, it'll have many possible states, but we can isolate 2 of those energy states, and we can either put the atom in a state we might call 0 or a state we might call 1, but we can also put it in superposition states where it's both in the lower energy level and the upper energy level at the same time. And that's very much like the box where it has both properties at once. So where does Schrödinger enter this? Well, Schrödinger, of course, is one of the inventors of quantum mechanics, so-called wave mechanics. And when the early founding fathers of quantum theory were discussing these issues, like Schrödinger and Einstein and others, they could conceive how it worked on small systems like atoms and so on, but the idea, or the conclusion they came to, the equations that describe quantum mechanics, they can write them down easily for atoms and so on. But in principle, they should apply also to very large systems. And this was very dissatisfying to Schrödinger, and the way he chose to express his dissatisfaction was an example of a cat. And so he cooked up a kind of a macabre example of to show this macroscopic superposition. And that was, he said, suppose you have a cat in a box, a sealed box, so it's not perturbed by the outside world. And you also have a single radioactive particle. And suppose that the situation is made so that if the particle decays, it releases it triggers a mechanism which releases poison and kills the cat. Well, if in principle we could, it would be impractical, but in principle we could write down the quantum mechanical equations that describe this situation. And all we can say is that without disturbing the system, is that after a time that's given by where the probability of decay of the radioactive particle is about 50%, then all quantum mechanics tells us is that inside the box the situation is that there's a superposition where the particle is not decayed and the cat alive, and the particle is decayed and the cat is dead. So there's this superposition state. And this is typically called, I won't talk much about entanglement, this is an example of what's called an entangled superposition, where the two properties of two systems are correlated in this way. But anyway, the main result of this thought experiment that Schrödinger had was that quantum mechanics naturally led to this situation, which seems totally unreasonable. But anyway, but this problem has existed ever since 1935 when Schrödinger came up with this example. But later in his career, he said, he made the statement, even though these thought experiments, thinking about the effects of quantum mechanics on individual systems like atom and molecules, they thought they understood that, but he says, in fact, at least in 1952, we can never experiment with single electrons or atoms. And thought experiments we sometimes do, but that invariably leads to ridiculous consequences. What he meant was his cat. Well, in fact, at least nowadays we can. I mean, these thought experiments are the world we can play in, and in fact, we can do carry out these ideas at least with small systems. The examples that we work with in our lab are atomic clocks and this idea of quantum computers. I'm only going to talk about the computers here, but they sound pretty different, but they involve the same kind of physics. And as I said, with apologies, I'm going to give you kind of my story of how I got involved, but there's many people around, and many groups around the world working on this. And again, what we're going to need is we're going to be able to create superposition states, and we need to manipulate individual quantum systems and exert control over them. So let me give you an idea how I got into this business, and it was always, since I was in school, it was working with the ingredients necessary to make a quantum computer. So I was a student at Harvard, and from 1965 to 1970, and this was my professor, Norman Ramsey here, was a famous atomic physicist, and this is actually me trying to get close to the boss here, you see. Anyway, but my project at this, as a graduate student, was to make what's called a maser, and this is based on atomic deuterium. And a maser is like a laser, but M stands for microwaves rather than light. And the principle is just the same. But one of the attractions for me was that you could do very high precision measurements. So this oscillation so-called hyperfine oscillation in deuterium was at this frequency here, which you can see is very precise. And so, and what was required to get such precision is you needed very precise control of the environment that the deuterium was in. And I guess what this kind of thing really attracted me, the kind of detective work you go into controlling the environment. Also, as a byproduct of this, the deuterium atoms, when they're inside this maser, they're radiating, but they're in a superposition state. And actually, on typical scales, the superpositions last fairly long, about in a second in this maser device. So then after getting my PhD, I went to the University of Washington and worked with Hans Steenmalt. And anyway, the experiments he was working on is he was storing both electrons and atomic ions in what we call a trap. And I schematically represent what this is meant to represent. Very schematically are the blue lines here are the electrodes of a structure that we apply electric fields to, and we can grab onto the charge of the electron or the ion and hold it in one place. And again, the analogy you want to think about is if we have several electrons in this device, it's again like the marbles in the bowl that can roll back and forth. Now, in fact, this acts like a circuit element, and we can put it in a circuit like this. If you don't understand this, don't worry. But the key thing is that we can force the oscillation of the ions, and by doing that, we can pick up a current in one of the electrodes, and we can put it across a resistor, and it turns out the voltage that we read out is proportional to the number of electrons in this experiment. And the reason that was important was that Hans Steenmalt, one of his main projects for many years was to try to measure the magnetic moment of the electron. And the basic statement there is that the electron, in addition to having a charge, it behaves like a tiny magnet. And one of the interesting things in terms of quantum physics about this is that the theorists can predict the strength of this magnet that the electron carries to about 12 digits. And in fact, it's the most precise calculation that can be done with quantum mechanics. And so there was a great impetus to try to measure this magnetic moment very precisely. So, and it turned out as the experiments went along, it was clear that the way to get the highest precision was to put a single electron in this device. And the reason for that is simply if you had more than one electron, they would bump into each other and perturb the measurements on the electron. So in fact, my project when I was there was to try to isolate single electrons. And so in this same experiment I described, actually the experiment, at least conceptually, was fairly straightforward. We would cause the ions to oscillate back and forth in this bowl, and we'd excite them to such a level that occasionally one would fall out of the trap, go over the edge, and we'd see these steps in the number of electrons in this case that were in the trap. And of course, eventually we'd lose them all, but we'd to be able to experiment on single electrons, and we'd stop before the last one went out. And anyway, this was, as I said, a precursor to this accurate measurement of the magnetic moment. But for me, it got me into thinking about single atomic particles in my later work. So I went to after doing a postdoctoral appointment at the University of Washington there, I went to the National Institute of Standards and Technology, which was then called the National Bureau of Standards. And when I was at University of Washington, I had, with my advisor, Hans Steenmalt, we had an idea of how you might actually use lasers to cool atoms down. I mean, we're probably more familiar about how lasers can be used to heat things. For example, a strong laser can be used in welding, but in fact we can use. We thought of a way that when you shine laser on an object, in addition to it may cause heat, but one thing it does is it causes a force. And, you can think of the photons hitting an object and applying momentum to them. Well, we can range the frequency of the lasers to actually retard the motion of an atom when it comes towards the laser. And in fact, this idea is important in the atomic clock business. This is a cesium clock where the atoms go through this long tube, and when they go through, we measure their oscillation frequencies. But one of the things that we have to worry about in very precise clock measurements comes from Einstein's theory of relativity, where if in different reference frames, say moving relative to each other, what Einstein told us was that time runs at different rates. In these experiments on atomic clocks, when we send atoms through this device, time is running slower for them relative to us in the lab. And it's a very small effect, but we have to worry about it, because of the high precisions we get. And so the idea was, if we could cool the ions down, slow them down, then we would suppress this effect, this uncertainty. Well, anyway, so my boss at that time, Helmut Helvig here, anyway, he got us some support to try out this idea of laser cooling. And this was important for me personally because it was the first experiment that I was kind of in charge of. And it turns out now to be a fairly ubiquitous thing, a common thing in atomic physics. And anyway, so we set out an experiment to show this idea of laser cooling. And what was interesting was that I knew my postdoc advisor had gone to work in another group, Peter Toshek's group, who was then in Heidelberg, and I knew they were trying to do the same experiment, and we were trying to do the same experiment as well. I'm pretty sure they didn't know about our experiment. I didn't know at what point they were in their experiment. But what's interesting is you can see our paper was published a little earlier than theirs, but to be fair, when the journal received the paper, they were actually one day earlier than us. And this was an amazing near coincidence, because normally in physics, most of science, if you do something within a few months of each other, it's a tie. But this was almost a dead heat here. Anyway, so in our experiments, just coming back, if you think about the electron experiments where we could sense a current that gave us an idea of the energy and the number of ions in the trap. In this case, we used a very similar idea, but the thermal oscillations of the ions in the trap, they would also induce currents in the electrodes, and we could measure those. And those thermal currents were a direct measure of the temperature. So the way we could determine the temperature in these experiments is we just measure this current, and when we turn the laser on to do the cooling, the temperature would go down, and after we turned it off, eventually the ions would warm up due to electric fields in the background. Anyway, so this was our entire group shortly after those experiments. And always the embarrassing part for me is here's a more recent picture, and my friends here, Jim Berquist and Wayne Atano, they pretty much look the same, but these other guys kind of show their age, I'm afraid. Anyway, so let me give you an idea of some of the experiments we do, and I'm going to describe these. These experiments the experiments we do are very similar for atomic clocks and quantum computers, but I'm going to focus here more on the application to this idea of quantum bits and quantum computers. So anyway, I haven't really described the details of this cooling process, but the experiments we have are, this is a schematic of the electrode structure. You can see it's fairly small, about 1 millimeter across this inner dimension, and we put these devices in a vacuum so that the background gas molecules won't collide and interfere with the ions in the trap. Anyway, as I said, I won't go into the details, but we apply a combination of electric oscillating and static fields to hold on to the charge of ion. Anyway, with this laser cooling, even though the ions, if we didn't do anything, they would reach a thermal temperature of room temperature. With this laser cooling, we can cool them down to about a thousandth of a degree absolute in terms of Kelvin. Anyway, so when we shine this laser on that does the cooling, it's in the ultraviolet, and we can actually make an image of this with an ultraviolet sensitive camera. You can kind of make out this electrode here. There's some scattered light there, and you can kind of make out the inner part of this, what we call the ring electrode. And in the center, that's a single ion. And one thing that's kind of interesting, the size of this image of the ion, it's limited by just what's called the diffraction limits, just by the quality of the optics. And in fact, we can show by other means that actually the size of the wave packet that describes the atom is about 500 times smaller than this. So it's a really bright, if we could see at that resolution, it's extremely bright, and it's kind of smeared out due to the limited optics. And although the ions we use, they only emit scatter light in the ultraviolet. There's some ions, for example, barium, that scatters light in the blue that you can. And I've been in some labs where other people are working with barium ions, and you can actually see a single atom, a single ion with your eye. It's fairly faint. It looks like a faint star, but nevertheless, you can actually see it in one of these apparatuses. Okay, so there's another set of energy levels in the mercury atom, and the nice thing about this one is if we excite the atom from the lower state, which we'll just label a 0 and 1, in thinking ahead about our quantum bits here, is that this level here will last for a fairly long time. So, in fact, we can, by shining a laser at the right frequency, if we start the atom in the lowest state, say the 0, we can actually make one of these superposition states and make it be a quantum bit. Now, in fact, how do we do the measurement? And the idea is that we can alternate. If we first apply this laser and then we turn on this laser that does the cooling, since we can see the fluorescence, the scattered light from this laser, we can, if the ion, when it's measured, if it remains in the 0 state, then we see scattered light on this transition here. On the other hand, when we do the measurement, if the atom is projected, we say, into this upper state, then there's no scattered light here, and we can easily tell the difference then which state the atom, which of our quantum bit states the atom is in, by looking for the presence of fluorescence or not. Okay, so one other ingredient I need to include here before we talk about, give you an idea how we make a quantum computer, is that we also have to think about another set of energy levels. Now, when I've talked about our atomic marble in this bowl, I've talked about it in classical terms where it can oscillate back and forth, but we know quantum mechanics also tells us that, in fact, no, it doesn't exist in a continuous range of energy levels. It only exists in a discrete energy levels. And in fact, we say these oscillation states are quantized, and they can only exist in certain discrete energy states. So in fact, we have a ladder of possible states of quantum states that the motion is in. And one difference is here that the difference in energy levels, say, of the ground state and the first excited state of motion is about 1 billion times smaller than the energy separation of the electronic energy levels that we're going to make our quantum bit on. But anyway, we can, without, again, going in the details, we have a kind of a second version of laser cooling where we tend not to talk about temperature, but we we talk about which energy level we can cool the atom down to. And so in this example, this second version of laser cooling, we can actually put the atom in the lowest possible state of motion, called the quantum ground state. And this corresponds to a temperature of about 100 times lower than what the normal laser cooling does. But the key thing is that, more importantly, is we can actually precisely put it in one of these energy levels. And in fact, it's not to say that the atom is at rest. One of the other features of quantum mechanics we learn about is from what's called Heisenberg's uncertainty principle, which in this context says if you try to hold the atom in one place, it still jiggles around with a certain amount of energy. And there's sort of a compromise where you can confine the atom to a certain dimension and also restrict its kinetic energy to the lowest possible values, and that's called this quantum ground state. So it never loses kinetic energy, but it's the lowest possible amount of energy which satisfies the rules of quantum mechanics. Okay, so now I'm going to try to get, with those ingredients, I'm going to try to give you a simple idea of how the quantum computer might work. The hard part is we can, by tuning, if I go back to this picture here, we can easily change the state of each quantum bit by shining a laser, and we can also make the superposition state. The hard part is how do we make a quantum gate between two quantum bits. And let me first say that the part of this is not so. If you've done any programming at all, the kind of programming we think about is very similar to how you would do program in Fortran, for example. It's just to make a general quantum computation. We either think about changing the state of each of the individual quantum bits, say doing a bit flip, and then we do logic gates between two separate quantum bits to do the multi-qubit gate operations. And in fact, any classical computer can be based on those two operations. And similarly, we can make a general quantum computer based on just the single bit transitions and combining two bits to make a logic gate. So I'm going to try to give you an idea, at least a sense of how we make these logic gates. So anyway, not long after Peter Shor's algorithm, the interest in this subject really exploded. And actually, one of your countrymen, Ignacio Serac, who was then working with a well-known theorist, Peter Zoller, they understood the basic ideas of how you might make a quantum computer. And they were also, to their credit, they're very well aware of the kind of experiments we could do. So they very quickly came up with an idea of how you might make a quantum computer based on atomic ions. So the idea is it has the same ingredients I've tried to describe to you here before. But now let's see, let's suppose we have, now I've changed doesn't look like the bowl, the simple trap anymore, but again, you can think about this as this electrode structure. It makes a three-dimensional bowl that we put our atoms in, and we configure the strength of the fields in different directions so that the atoms all want to line up on a single axis. So you can, along this horizontal direction, you can think of an atomic bowl that kind of looks like that, and all the atoms want to fall to the bottom of the bowl, but the Coulomb repulsion between the charges of the atoms holds them apart in this regular array. And the reason that's nice is we can address them with laser beams. So anyway, I'm going to try to give you a rough idea, the overall view of their notion of how we might make a quantum computer, and then give you a little bit more specifics of how we carry out the operations. So just as I explained that with this second version of laser cooling, we can cool down the motion of a single ion to its ground state. Well, in fact, say in this example with 5 ions, you can think of this kind of like it's like a molecule, a pseudo-molecule that we've constructed. And it has vibration, normal modes of vibration, we say. And the simple one in the context I'll describe here is what we call the center mass mode, where in this case the 5 ions are oscillating back and forth in this external potential we created. Now, using the same ideas that we applied to a single ion, we can actually cool any of these modes of motion down to the ground state. Now, and once we do that, then the interesting part is that the ground motional state and the first excited state of motion, we can treat those as another quantum bit. And so the idea of Ignacio and Peter was, suppose this ion here is in some superposition state, and I represent that pictorially by drawing heavy lines. In other words, both of the states are occupied here. And they suggested, well, if you can somehow map the superposition state of the electronic states of this qubit into this motion state qubit. The interesting part about that is this, again, in this particular example, the motion qubit is shared amongst all the ions. So they all sense the motion state, even though we only addressed one ion here. Because they're all locked together, they all feel this, they all experience this motion state superposition. And then the second part of their proposal is if you can somehow then make a logic gate between the internal states, the electronic states of this ion and the motion states of this ion, then you basically made a gate between the two selected ions through this mapping process. And then the final step would be then you, after doing this quantum gate, you would map the motion qubit back into the internal state of that ion. So that's the procedure, and there's some subtleties here, but just to give you a rough idea of how we can actually do this. So for this first step, this mapping step, we can take a laser, and if the ion is, suppose this ion here is it's initially, the motion is in the ground state. And then if we can somehow, so this level is occupied, or this amplitude is occupied, and so is this one. But if we can take a laser and tune it to the right frequency so that we completely transfer the amplitude of this state down here, then we've done this mapping step that I described. And then in the second part of it, it's a little bit more complicated than what I'll describe, but it gives the right flavor, and that is, so suppose we want in a 2-bit logic gate or a 2 quantum bit logic gate, we want to realize some truth table. And the elements I'll describe here is that the motion qubit, which is now, it can be either in the ground or first excited state, we'll call that the control bit, and the part of the logic table I'll present here is that when the motion qubit is in the 1 state, we want to be able to flip the bit, the electronic bit. On the other hand, if it's in the m equals 0, the lowest energy state, then we don't want the bit to flip. And the way we carry out this part of the truth table is, again, pretty simple. If the motion is in this state here, then we tune a laser so that we can transfer this state up to here. So in other words, we flip the internal state of the qubit. But that same laser beam, if the ion is in this lower state, there's no place for it to go up here. And so, in fact, the electronic state doesn't change. So anyway, that gives you a rough idea of how this, we call this conditional dynamics, but it's how we can make logic gates. And that's as complicated as I'm going to get here, but I wanted to try to give you an idea of how this works. And basically all these operations, especially between 2 bits or multi-bits, rely on what we call this conditional dynamics. So anyway, one nice thing in our lab is we were, Chris Monroe, who was earlier a postdoc in our group and then went on to later establish his own group, we were well aware of Ignacio Serac and Peter Zoller's proposal, and it turned out we had been trying to do some things that are now called quantum logic, but we were well poised, and so we could jump on this idea. And so within matter of about a month and a half, we could demonstrate the logic gate that was proposed by Ignacio and Peter. But again, let me say that this is just what our group is doing. This give you an idea of the scope of things. So just groups around the world that are just using atomic ions to realize these ideas of quantum computation. You can see there's a huge number of groups around that are pursuing this problem. So we're not the only ones. There's a lot of good groups doing good things. And in fact, there's many physical platforms on which we might make a quantum computer. And I list a couple of these here. These may not make any sense. Actually, one of the more advanced one is based on Josephson junctions, superconducting electronics. But you can also, but again, they think about having two levels in their quantum system, and the kind of logic operations they do are very similar, but just based on different physical principles. So anyway, the basic message here is that there's a huge number of groups around the world working on this idea of trying to make a quantum processor, a quantum computer. One of the problems, just to give you an idea where we're headed, we can do some basic operations and we can string together logic gates. We can't do very many together right now. But one of the things we want to do is to scale the system up to a larger number of quantum bits. That we're making this doesn't look like the same trap at all. This one, though, one nice thing about this is the yellow part or the gold part here is actually it's gold that we use modern lithographic electronic techniques to put electrodes in a surface. On this one, the ions they work on the same principles. It doesn't obviously look like the same kind of trap, but in each one of these little tiny squares, we can hold ions above the surface out of the plane of the figure there, and we can do these operations similar to the example I gave with the proposal of Ignacio and Peter. And the idea here is that we can multiplex up this system in the way if we want to do a logic gate, but say between an ion bit here and an ion bit here, we apply electric fields and we shuffle the ions around, again acting on their charge, and we can bring those bits together to do logic gates. So that's an idea of how we're trying to scale up, and many other groups are trying to do similar things. And where's the future? Now, I mean, first of all, I would say we're still at a very crude stage. We can implement all the basic ideas of how to make a quantum computer, but right now the errors are just too high. And but on the other hand, the good news is we know what we have to do, what the problems are, what we have to solve to do this. So I think we're fairly optimistic, but having said that, I don't think you want to invest in any quantum computers yet. But I think one of the things that as physicists we're looking forward to, and this is just a very brief, I'm not really explaining it, but it turns out that when we do these logic gates, they mimic the interaction, say, for example, of two electrons in a solid. They mimic the interaction of two interactions in a solid. And in fact, one of the ideas is maybe we can, as we build up the number of quantum bits, maybe we can represent the interaction of many electrons in a solid. And this is a difficult problem in condensed matter physics. It's just computationally, it's extremely hard. But with a quantum computer, we should be able to efficiently simulate these systems. So I think this is where, as physicists, we're looking for the real first application, is to simulate other quantum systems of interest. And there's, I won't even describe, we're actually using some of the simple ideas of the quantum measurements in our atomic clocks, and we're already realizing some of the benefits of these simple ideas I mentioned to make more precise clocks. And much farther, the hardest problem anybody's thought about is this factoring problem. And it's the one that got the field going, but there's no question it's about the hardest problem anybody's thought of. So that may be a long ways away before we can do that. And as with most new subject in physics, there's probably applications we haven't thought of. And an example that's always brought about this is when the laser was first invented. It was more of a toy, and nobody really had any idea what the uses would be. But of course, as you know, the lasers are ubiquitous in our society today. So we hope that same story might be true for these ideas of quantum information. So let me just, before I'm going to, at least the technical part, let me just conclude by saying one thing. Now, in fact, we can make states, different kinds of superposition states. In this example I'm showing here, it's a superposition state where if we have, say, n qubits, we can make them where they're all a superposition where they're all zeros and all ones. And the interesting part about this related to Schrödinger's cat would be that if we can make the number large enough, we can do this with small numbers up to about 10 or 15, but if we could do it for thousands, then it turns out our quantum bits, each one behaves like a little magnet, like the electron. And if we put a bunch of these together, we can think of a more macroscopic magnetization, like a small piece of iron that would be magnetized. And so, in fact, the kind of experiment we can think about schematically, we could take off one of these quantum bits, say the first one, and we could put it in one location, and then we leave the other group of ions in another location where we have this more macroscopic magnetization. And we would say this is really like Schrödinger's cat in the sense that here what was the radioactive particle in the cat example was this one isolated atomic ion over here, and then the cat would be more like this more macroscopic magnet that has this larger scale property. And you might argue, well, this is too simple, but I think it does have all the ingredients of a Schrödinger cat. So if we can exercise the control we want in the future, I think we are making analogs to Schrödinger's cat. So with that, as I say, there's many groups around the world. I was certainly lucky to work with a good group of people that I mentioned my colleagues in that earlier view graph. Basically, one nice thing is we've been working together our whole careers on these and related problems. There's been newer members of our group that have joined since that I show pictures of here. I've been lucky at NIST to have good bosses, and in fact, my boss 2 levels above me, Catherine Gebbe, she was the leader of what's called the physics lab at NIST for 20 years, and one measure of her success is I'm actually the 4th person under her leadership to win the Nobel Prize, and so she's been really a great boss for our whole laboratory. So let me say a little bit about the Nobel Prizes. It's a surreal experience for any normal person like myself. One interesting thing is, as you probably know, the awards are announced in early October, and then the award takes place in early December in Stockholm. And there's many funny stories I could tell, but one thing, they announced the award in Stockholm at 11:30 in the morning. Well, it's 3:30 in the morning in Colorado, so that's when I got the call. And actually, for me, I was sound asleep, and my wife luckily woke up to the phone. I would have slept through. So anyway, going back, so in early December, this is close to Christmas, of course, and Stockholm's a really a very charming city, and they have these outdoor fairs. One thing you can see here, there's snow on the ground, and it is cold, but yet people are outside and they just wear a lot of clothing. And the other thing to notice is actually this picture was taken about 3 in the afternoon, and so it gets dark there very early. And then, so there's all kinds of festivities, and the main ceremonies are held in the concert hall. And the awards are presented in a very fancy way. This is the royal family here, and the front row here was the laureates that year. There were 9 of us across various fields, and anyway, the king presents the award to each one of us, so this is a picture of me receiving the award from the king, and I must say the thing that I was most worried about was that, of course, they have a very standard uniform we all have to wear, which included patent leather shoes, and it was almost like with these shoes I felt like I was walking on ice, and my whole focus when I walked out to greet the king was don't fall down. Anyway, I didn't fall down. It went pretty smoothly. Anyway, after this main ceremony, then the king and queen invited a few people over for dinner. So this is the main banquet after the awards ceremony. And actually, one thing you find out is there were 9 of us laureates, and one unfortunate thing is that we're only allowed to invite 12 guests to these main functions, and so I mean basically that's 100 people. Well, there's 1,400 people at this dinner, and what you learn is that this is probably the biggest social event in Stockholm every year. So it has a number of government dignitaries and other important people, and they're nice enough that they invite a number of students as well, but it's a very, very big deal and very fancy. In fact, the way the meal was served, there was, I don't know, 100 waiters, at least hundreds, it was all choreographed, and in fact, one of these guys here, he was like an orchestra leader, and he would direct the waiters so that basically all 1,400 people were, in groups of 5 or 6, they were all basically served at the same time. And so it was an amazingly well-organized thing. Anyway, it was a wonderful experience, as I say, almost surreal, because it was just something way out of my ordinary day experience. Finally, let me say one really nice thing was the person I shared with, Serge Haroches from Paris. I got to know him. Well, I got to know his physics about 35 years ago, and then I became friends with him about 30 years ago. And in the meantime, our wives have become friends. So, we've done some things outside of physics, and it was particularly nice to be able to share with him because of this long-term friendship. And finally, let me just conclude by saying, again, emphasizing this, it's not individual effort. I just show you that this is the size of our current group. First, we started out with 4, but you can see it involves a lot of postdocs and students and visitors. And of course, these are the people doing the work. So with that, I'll stop, and thank you.
So, thank you very much, David, for this fantastic excursion, I would say, into this complex world of quantum computing. Tenemos tiempo para algunas preguntas. Estáis todos invitados a abrir el diálogo, a hacer cualquier pregunta, en inglés o en castellano, intentaré traducir.
Yeah.
Gustavo?
Oh, go ahead.
Okay, sorry.
For the working of the quantum computer, at some point you have to stop and measure the state of the computer. So at that time you introduce perturbation in the state of the computer. In the analogy of the Schrödinger cat, maybe you kill the cat, and you want to start again a new computation. So how hard is to stop the computer, measure, and prepare again the computer to work on a new problem?
Well, it actually turns out to do the measurement and stop the computer and then prepare it again for another computation. That's the easy part. And in fact, we do that. We can do that with enough bits to factorize a large number. But as I mentioned before, the key problem is the logic gates that we make. They're noisy, and so there are errors which are too high to be able to carry out a large computation right now. And there's no magic. The errors are in all the different kinds possible implications. I think we understand what the errors are. For example, in our experiments where we manipulate the quantum bits with laser beams, one of the very simple problems we have is that the intensity of the laser beams will fluctuate. For example, well, there'll be quantum noise, but there'll also be things like, at least in the experiments right now, we propagate through air, and there's fluctuations in the air currents that cause fluctuations in the beams, which cause intensity fluctuations. So it's as I say, we know what the errors are, and then sometimes it's harder to fix them, but we do know what the errors are, and so we just got to keep working to beat down these various problems. So.
Thank you very much for the talk. I have also a question concerning to the quantum computers. I wonder whether to have more and more qubits is just a matter of technological improvement, or if, on the contrary, there is some theoretical limitation for the number of qubits you can have in a quantum computer.
Well, again, I'd probably give a similar example I just gave. And in fact, we can make a quantum register that has 1 million qubits. And in fact, we can make this entangled superposition where 2 to the million qubits are entangled. We make a superposition state as similar to the one I indicated for 3 quantum bits. So we can handle a very large number of quantum bits, but again, the key problem is when we make the logic gates between 2 selected qubits, the errors in these operations are just too high right now. So that's the key problem in all the physical implementations, is that when we do the gates between 2 quantum bits, there's noise in the system, various kinds of noise that different ones for the different possible implementations. But those are the key problems, I would say.
Thanks.
Could it be that the real cut is so big that the noise actually makes it impossible to be quantum?
Well, this to answer this fairly is the subject of long debate, which has been going on since Schrödinger, and so no, but it's a very good question. In fact, one of the interesting things, if there is the problem of noise, and that's I think the problem and that is there's this technical problem, but interestingly, and it's I think what Schrödinger was trying to say, at least in principle, you could make these very large superposition states. And if you extend this idea beyond what Schrödinger was talking about, it leads into the idea of many universes, many worlds. That is, that basically all quantum mechanics tells us is that there should only be these huge superpositions on the scale of the universe, and so that's what leads to these ideas of many universes. And all I would say is that we can't disprove that idea, and there's many practical reasons why we can't make large superpositions, but fundamentally, that's quantum mechanics tells us that these many universes should exist. Now, you can. At this point, you have to, it becomes philosophy, right? I mean, I don't just personally, if this idea of many universes is real. I mean, there's a hideous number of parallel universes, and I'd like to believe the universe is a little simpler, but I don't have any reason to really justify that statement. But let me just add one thing, is that in fact, one thing people think about is maybe there's some mechanism in physics, some that we haven't identified yet, but that prevents large superpositions, some sort of collapse mechanism which is physically real, but we haven't seen it yet. So that would solve this problem of why there isn't cats, and maybe kill the computer too. But anyway, I mean, that would be a fantastic discovery in itself, even more interesting than quantum computers if we could find this mechanism. But it's just conjecture so far.
Epa, nik galdetu nahiko nuke ia nola azalduko zenioken gazte bati, adibidez bigarren hezkuntzako ikasle bati, zer den ordenadore kuantiko bat, eta nola den posible eraikitzea. Erabili barik hain komplikatuak diren formulak ero azalpen batzuk. Era errez batean, konparatzeko beste gaur eguneko ordenagailuekin. Eskerrik asko. ¿Bai? ¿On bai? Quisiera preguntar, gracias, quisiera preguntar a ver cómo se le podría explicar a una persona de educación secundaria, por ejemplo, qué es un ordenador cuántico, cómo se haría para que lo pudiera entender sin fórmulas tan complicadas y que se pudiera comparar con uno que él conoce hoy día. ¿Cómo se podría hacer eso didácticamente?
So the question is whether you could explain, let's say, what a quantum computing is to a child, to someone who is in primary school, let's say, without using these complex formulas.
Oh boy!
And how to do that?
I'm not sure I know the answer. I struggle to, as you see, with I've tried to make my presentation as simple as I can. But I think one thing to say is that, one of the difficulties is, I mean, there is this very strange world of superpositions. It doesn't make any sense in our ordinary day experience. For example, to have a marble be both on the left side of the bowl and the right side of the bowl at the same time. I mean, it's, it makes no sense. So in that sense, in that same spirit, I mean, it's hard to try to explain how a quantum computer, because it relies, a key idea is that it relies on these superpositions. So I don't know, but maybe you can help me. It's a tough job. So.
However, you started your beautiful talk with an example of superposition, the Necker's cube, which should be very intuitive. It's beautiful, to the point that I'm tempted to ask: is a visual perception following quantum logic rather than? Obviously, our brain is not a Neumann computer, so something else.
So I may
this example of the cubes, which have two different ways of being seen. So you have an oscillation between the two. This is an example of superposition. Fantastic. But this is an effect of our visual perception, the way our brain works.
Right.
So can we learn anything about the logic of our brain, namely whether it follows a quantum logic rather than, I don't know.
Well, that's probably an answer for our young people to answer. But no, having said that, I think, the tentative answer, most people feel that that superposition, if it plays a role in our brain, it's probably a small role. That is, at least the notions, and I'm no expert in this, but I think most people's notions about how the human brain works is it's more classical logic, that like like the bits in our computers. They're either zeros or ones, that sort of thing. Having said that, one active area of interest right now is, can there be superpositions that describe anything in life? And one of the interesting things is both theorists and experimentalists are, when they examine photosynthesis, one of the ideas being discussed now is that when light is received, I'm not at all familiar with all the energy transfer processes in photosynthesis, but one of the postulates now is that this energy transfer in photosynthesis from light into the molecules that store the energy is so fast that the only way that people can seem to explain it is there has to be this what they call coherence, but it involves superpositions. So that would be, so we're just touching on that, and it's possible maybe that plays a role in our brain too. But yeah. But these ideas are just starting now. It was, yeah.
As you said before, you use the laser to cool down the qubits so that the activity is slower. So if inside the computer the activity of the qubits is slower, how does this make the computer to be faster?
Well, it's not so much a question of speed. That, in other words, in fact, the logic gates we do are typically, even now, they're typically a few microseconds when we do these logic gates. So that's very slow compared to our normal computers. But it's more this idea, and it's hard to get an idea across in a short time, but it's this idea of exponential scaling. The fact that when we make a memory out of n quantum bits, it represents 2 to the n possibilities. Then that's an example. And this idea of parallel processing, that's where the advantage comes. But to come back to your question about the cooling is basically, well, in the idealized version, what we do, we want to do the cooling because we want to prepare the motion energy states in the absolute ground state. And then from there, we do these operations that I tried to give you an idea. So the cooling there is important just to get down to the lowest quantum states of motion in the kind of scheme we're looking at.
Thank you.
Sí, en cuanto al dilema del gato de Schrödinger, parece que solo cuando tomas conciencia de, cuando abres la tapa y tomas conciencia de que está el gato, es solo cuando existe, es cuando tomas la conciencia. O sea, que parece que la conciencia tiene un papel fundamental en cuanto a tomar forma, la partícula a nivel atómico, se forma como partícula cuando tú tomas conciencia de ella. ¿Es así?
Whether, let's say, for this Schrödinger's cat, so one actually, let's say, the cat can be alive or dead depending on whether you are measuring that or not. So it's at the moment in which you measure that let's say, you realize which is the so
right.
Is this correct?
That's right. So it's just as I was trying to say, for a single bit, when we make the superposition, before we do the measurement, it's both a 0 and a 1 at the same time, and then when we measure it, it's either a 0 or a 1, not both. And so the idea with the cat is very much the same, just on a much larger scale. That is, before we do the measurement, the cat is both alive and dead, and then when we measure it, it becomes one or the other. And so.
Okay, if there are no more questions, I think we can close here. Vamos a acabar entonces. Thank you very much again, David. So, this is really the end. So this is really the end, you see. So I was going to say thank you very much again, David, for this wonderful lecture. It has been a privilege for us to be all this week with you in DIPC. Y gracias también a todos vosotros por haber venido. Nosotros como... Yeah, sorry. Yeah.
Friday night and you could be doing a lot more fun things, but anyway, thanks for coming.
Sí, yo lo que iba a decir es que nosotros como... Que nosotros como científicos estamos convencidos que es nuestra obligación el compartir con todos nuestra actividad, es nuestra responsabilidad y estamos convencidos de ello porque nuestra actividad solamente tiene sentido en tanto y en cuanto la sociedad cree en ella. Y por eso es muy reconfortante organizar actividades como esta y ver pues, que hay una respuesta como la de hoy, que teníamos la sala llena. O sea que muchísimas gracias a todos por venir hoy, un viernes por la noche, como decía David.
Sorry.